So today we're going to be presenting a little paper on differential steering control with proportional controller for an autonomous mobile robot. So in terms of mobile robot, it's very difficult for movement in domestic environments because mostly because of the uncertainty and the position of things that are bound to change. And so something as simple as moving in a straight line is very essential. It's also very difficult to do. So in order to achieve this, the paper proposed a closed loop sensor with a proportional controller. Now, the mobile robot, as we can see in figure 1, contains two driving wheels that are powered each by independent DC motors, and the center of mass is assumed to be in the middle of those driving wheels. So, in order to control that robot, we're going to be using a proportional controller, where E is going to be equal to SP minus PV. E is the error, SP is the set point, so the value that we want, and PV is the process variable, so the value that we have right now. Now, below that, you can see the full equation for PID controller. This paper is only interested in the P side of it, so we're only taking U of t equals Kp times the error. So this means we only correct the error by a portion of it. Small error, we're going to apply a small correction, and the big error, a big correction. Now, the results of the experiment that done, well, the first one was done without any disturbance environments like floor, so the wheels spinning in the air. And for a range of values between 0.1 and 10, we can see that anything above 1 was ignored because there wasn't really any change. And we can see that there's a small difference between the two wheels. So in the second experiment, the values were fine-tuned a little bit more. Range is going to be a lot smaller, from 0.01 to 0.1. And as we can see in figure 6, we require first a value of 0.03 to even get any of the wheels to start moving. And we can see the best results are between 0.07 and 0.09. In the third experiment, it was done to replicate practical application. So it was done on a floor, moving at a distance of 100 centimeters. And as we can see in figure 7, 8, 9, they show the best results of the tuning parameters. And we can see a little bit that 0.07 and 0.08 can perform the best, although 0.07 has that slight extra bump in the middle. In conclusion, things to consider in these types of application is the sensitivity of the encoders that are used to measure the speed. There's a possibility of unequal wheel diameter or the misalignment of wheel that can lead to making it hard to go in a straight line. There's also wheel slippage that measure movement and speed when actually no movement is made. And for possible improvement, a full PI or PID controller could be used.